There's something out there in the vast emptiness of space, something invisible, mysterious, and overwhelmingly powerful. It's not a black hole, not a distant galaxy, not even some undiscovered planet. It's a force so strange that it defies everything we thought we knew about the universe. Scientists call it dark energy, and it's tearing the cosmos apart at an ever-increasing speed. Imagine this: the very fabric of space itself is stretching, expanding faster and faster, as if some unseen hand is pushing the universe toward an unknown destiny. And here's the most unsettling part: we have no idea what dark energy actually is. Welcome to the cosmic dark energy era, a chapter in the story of our universe so baffling that it keeps even the brightest minds awake at night. For centuries, we've looked up at the stars and wondered about the forces shaping the cosmos, but nothing has challenged our understanding quite like this. Dark energy wasn't even discovered until the late 1990s, and since then, it's turned astronomy upside down. Think about that: less than 30 years ago, we didn't even know this force existed, and now it's believed to make up nearly 70% of everything in the universe. That's right, most of reality is something we can't see, touch, or explain. So what do we really know, and more importantly, what don't we know? That's where this journey begins. Over the course of this video, we'll dive deep into 25 of the most mind-bending mysteries surrounding dark energy. From the way it warps the fate of the universe to the eerie possibility that it might not even be a single force at all, we're going to explore the questions that keep scientists guessing. Some of these mysteries could rewrite the laws of physics. Others might hint at entirely new dimensions or hidden layers of reality. And if we're lucky, by the end, you'll walk away with more questions than answers, because that's how real discovery works. Ready to step into the unknown? Let's begin. If dark energy is the universe's most dominant force, then its origin is its best-kept secret. Picture this: an unseen driver pushing the cosmos to expand faster and faster, yet we can't even trace where it came from. Unlike stars or galaxies, dark energy leaves no fingerprints, no light, no particles, no detectable signature. It's as if the universe itself is hiding the answer from us. One leading theory points to vacuum energy, the idea that empty space isn't truly empty. Quantum physics tells us that even a perfect vacuum crackles with fleeting particles popping in and out of existence. These tiny fluctuations might generate energy, but here's the catch: when scientists calculate how much energy this should produce, the numbers are off by a staggering factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It's the largest mismatch between theory and observation in all of science, meaning we're missing something monumental. Then there's quintessence, a far more exotic possibility. Imagine a mysterious field stretching across the cosmos, shifting and evolving over time, its energy waxing or waning like tides in an invisible ocean. Unlike the static cosmological constant, Einstein's once discarded idea that space itself has an innate energy, quintessence could change. Some models suggest it might even interact with dark matter or ordinary matter, weaving dark energy into the very fabric of reality in ways we haven't yet imagined. But observations keep throwing curveballs. Recent measurements of distant supernova and the cosmic microwave background don't always align with predictions. Some data hints that dark energy's strength might vary across time or space, which would upend our simplest explanations. Could it be that dark energy isn't one thing but many? Or worse, what if it's not even energy at all, but a flaw in our understanding of gravity itself? Every telescope, every supercomputer simulation, every bold new theory brings us closer to the truth, or reveals just how much we've underestimated the puzzle. The origin of dark energy isn't just a gap in our knowledge, it's a yawning chasm, forcing us to question whether we've been reading the universe's rules correctly all along. One thing's certain, solving this mystery won't just rewrite textbooks, it could redefine reality itself. For centuries, astronomers believed the universe's expansion was slowing down. Gravity, after all, pulls everything together, so it made sense that the cosmic tug-of-war between the Big Bang's initial momentum and gravity's relentless pull would eventually decelerate the whole thing. Then, in 1998, two independent teams studying distant supernova dropped a bombshell. The universe wasn't just expanding, it was accelerating. Imagine throwing a ball into the air, expecting it to fall back down, only to watch it rocket faster into the sky. That's how baffling this discovery was. The evidence came from Type 1, a supernova, cosmic explosions so predictable they're called standard candles. By measuring their brightness and redshift, scientists can calculate how fast the universe was expanding at different points in time. But these supernovae appeared fainter than they should have been if expansion was slowing. The only explanation, space itself was stretching faster than anyone predicted, pushing galaxies apart at an ever-increasing rate. The implications were staggering. Something dark energy was overpowering gravity on cosmic scales, and we'd completely missed it until now. But here's where it gets even weirder. If dark energy is truly constant, as Einstein's cosmological constant suggests, then its repulsive force should remain steady over time. Yet some observations hint it might not be so simple. Surveys of galaxy clusters and the cosmic microwave background suggest dark energy's strength could vary, weak in the early universe, stronger now. This would mean it's not a fixed property of space, but something dynamic like quintessence, shifting and evolving as the cosmos ages. The debate is far from settled. Some theorists argue that dark energy's apparent variability might just be an illusion, a trick of incomplete data or hidden biases in our measurements. Others propose even wilder ideas, like extra dimensions leaking gravitational force or modifications to Einstein's theory of gravity itself. Every new observation, from the Dark Energy Survey to the upcoming Nancy Grace Roman Space Telescope, tightens the noose around these possibilities or throws the door wide open to new ones. What's undeniable is that the accelerating universe forces us to confront how little we understand about the cosmos. Dark energy isn't just a mystery, it's a challenge to our deepest assumptions. If the universe's expansion keeps speeding up, galaxies beyond our local group will eventually vanish over the cosmic horizon, leaving future civilizations with a night sky almost empty of stars. It's a haunting vision, one that reminds us how much is still at stake in this grand cosmic detective story. If dark energy has been around since the beginning of time, why did it wait so long to take control of the universe? This is the coincidence problem, one of the most baffling quirks in modern cosmology. Think about it. For nearly 14 billion years, gravity dominated the cosmic scene, pulling galaxies together as the universe expanded. Then, relatively recently, astronomically speaking, dark energy stepped into the spotlight, flipping the script entirely. Why now? The timing feels suspiciously precise, as if the cosmos carefully scheduled this takeover. Here's what makes this so unsettling. Measurements show that dark energy's density and the density of matter in the universe are eerily similar right now. But they shouldn't be. Matter dilutes as the cosmos expands. More space means atoms and dark matter particles spread thinner. Dark energy, if it's truly a property of space itself, should stay constant. So why do their densities just happen to match at this exact moment in cosmic history? It's like showing up to a concert and realizing the band started playing your favorite song the second you walked in. The odds seem impossibly slim. Some physicists argue this isn't a coincidence at all, it's a clue. One controversial idea is the anthropic principle. Maybe the universe had to evolve this way for us to exist. If dark energy had dominated too early, galaxies never would have formed. Too late, and gravity might have already pulled everything into a cosmic crunch. We're here because the numbers lined up just right, but for many scientists that explanation feels like giving up, an admission that we live in a weirdly fine-tuned universe with no deeper reason. Others suspect dark energy isn't constant but evolves over time, interacting with matter or even itself in ways we don't yet grasp. Imagine a dimmer switch on a cosmic scale, gradually turning up the repulsive force as the universe ages. If true, this could solve the coincidence naturally dark energy didn't wait to dominate. It simply grew stronger as conditions changed, yet every attempt to model this behavior runs into hurdles. Why would the transition happen now after eons of quiet? Then there's the radical possibility that we're misreading the evidence entirely. What if dark energy's apparent dominance isn't a fundamental force but a side effect of living in an unusual pocket of the cosmos, or a sign that Einstein's gravity equations break down on the largest scales? The more we probe, the more the coincidence problem feels less like bad luck and more like a glaring hint that we're missing a huge piece of the puzzle. One thing's certain, the timing of dark energy's rise isn't just a quirk. It's a screaming anomaly. Whether it points to deeper laws, a multiverse, or flaws in our theories, it forces us to rethink everything. Because in a universe that's supposed to run on impersonal, unchanging physics, this level of cosmic convenience doesn't just defy odds, it demands an explanation. The idea that dark energy might not be constant at all, that its strength could ebb and flow like a cosmic tide, throws everything we think we know into question. For decades, the simplest explanation was Einstein's cosmological constant, a fixed, unchanging energy woven into the fabric of space itself. It's elegant, straightforward, but what if the universe doesn't do straightforward? Take the case of distant quasars, some of the brightest objects in the cosmos. Recent studies analyzing their light suggest dark energy's repulsive force might have been weaker in the early universe, only growing dominant over billions of years. This isn't just a minor tweak to the model, it's a revolution. If dark energy evolves, then the cosmological constant isn't just incomplete, it's fundamentally wrong. Enter quintessence, a theorized dynamic field that could explain these odd observations. Unlike the static cosmological constant, quintessence might interact with matter or even itself, its energy density shifting as the universe expands. Picture it like a rubber band stretching, sometimes snapping back, sometimes going slack, altering the pace of cosmic expansion along the way. Some versions of this theory even allow for dark energy to eventually fade, letting gravity regain control. But proving any of this is a monumental challenge. That's where missions like the Euclid Space Telescope come in. Designed to map billions of galaxies across 10 billion years of cosmic history, Euclid could detect subtle distortions in the large-scale structure of the universe, hints that dark energy's push isn't uniform. By measuring how galaxy clusters clump together or how light bends around invisible mass, we might finally catch dark energy in the act of changing. Even wilder possibilities lurk in the data. Could dark energy's apparent variability actually be evidence of extra dimensions leaking gravity into our universe, or a sign that Einstein's theory of gravity breaks down on cosmic scales? Each new observation tightens the screws on these ideas, but the truth remains maddeningly out of reach. One thing's clear: if dark energy isn't constant, then the universe's fate, whether it rips apart, crunches back, or something stranger, hangs on a force we're only beginning to decode. The next decade of astronomy won't just fill in gaps, it might tear up the textbooks entirely. What if dark energy is nothing more than a cosmic mirage, an illusion created by our misunderstanding of gravity itself? This radical idea turns everything on its head. Instead of invoking an invisible, repulsive force to explain the universe's accelerating expansion, some physicists argue we've been misreading the cosmos all along. The culprit, gravity, might not work the way Einstein predicted when you zoom out to the scale of galaxies and beyond. Enter modified Newtonian dynamics, or a theory that dared to challenge Einstein's relativity head-on. Proposed in the 1980s, Mund suggests gravity doesn't weaken as quickly over vast distances as Newton or Einstein predicted. In this view, the strange motions of stars in galaxies, usually blamed on dark matter, could instead arise from gravity's unseen quirks at low accelerations. But here's the twist: when applied to the universe's expansion, some versions of Mund also mimic dark energy's effects without needing it at all. It's like realizing the car you thought was speeding up was actually just rolling downhill on a slope you hadn't noticed. Yet Mund isn't the only challenger. Theories like F of R gravity, where gravity's strength depends on the curvature of spacetime, offer another way to rewrite the rules. Imagine space as a stretchy fabric. Einstein saw it as a fixed material, but F of R suggests its stiffness might change depending on how much it's warped. In this scenario, the universe's accelerating expansion could be a side effect of gravity weakening differently across cosmic distances. No dark energy required, just a tweak to the equations we've trusted for a century. But skepticism runs deep. Critics point out that while these theories can explain some observations, they often struggle with others, like the precise patterns seen in the cosmic microwave background or the way galaxy clusters collide. Dark energy, for all its mysteries, fits these puzzles more neatly, at least for now. And then there's the biggest hurdle. Einstein's theory has passed every test thrown at it on Earth and in the solar system. To abandon it for untested alternatives feels to many like swapping a flawed map for a blank page. The stakes couldn't be higher. If modified gravity is right, we're on the brink of a revolution as profound as when Newton gave way to Einstein. But if dark energy is real, then the universe is far stranger than we dreamed. For now, the debate rages on, fueled by every new galaxy survey and deep space telescope. One thing's certain: whether it's dark energy or gravity's hidden rules, the answer will reshape our place in the cosmos. Imagine a force so relentless that it doesn't just push galaxies apart, it shreds them. Atom by atom, this isn't science fiction, it's the Big Rip, one of the most chilling possibilities lurking in the shadow of dark energy. The scenario goes like this: if dark energy isn't just constant but grows stronger over time, its repulsive force could eventually overcome every binding force in the universe. First, galaxies would be ripped from each other. Then, stars would tear free from their orbits. Planets would disintegrate. Finally, even the fabric of matter itself, protons, neutrons, the very building blocks of reality, would be violently pulled apart. The cosmos would end not with a whimper but with a scream. The math behind this nightmare comes from a hypothetical form of dark energy called phantom energy. Unlike the cosmological constant, which remains steady, phantom energy would intensify as the universe expands, creating a terrifying feedback loop. More expansion means more phantom energy, which means even faster expansion until space-time itself can't keep up. Some models suggest this could happen in as little as 22 billion years. On cosmic timescales, that's practically tomorrow. But is there any real evidence this could happen? Observations so far offer slim reassurance. The cosmic microwave background and measurements of distant supernova don't definitively show dark energy strengthening yet. But they don't rule it out either. In 2018, a study analyzing data from the Hubble Space Telescope found a slight hint that dark energy's repulsion might be increasing, though the margin of error was too large for certainty. It's like seeing storm clouds on the horizon and wondering if they'll pass or unleash a hurricane. Critics argue the Big Rip relies on assumptions that stretch physics to its limits. For phantom energy to dominate, it would need a negative kinetic energy, a property so bizarre that it defies conventional thermodynamics. Even quantum field theory struggles to justify it without invoking speculative, untested ideas. And yet, the universe has surprised us before. Dark energy itself was unimaginable until we stumbled onto it. The stakes couldn't be higher. If the Big Rip is real, it wouldn't just mean an end. It would mean an end with no warning, no escape, and no remnants. No black holes drifting in the void, no atoms to build new worlds, just an infinite emptiness where a universe once was. That's why scientists are racing to pin down dark energy's true nature. Upcoming missions like the Vera Rubin Observatory and the James Webb Space Telescope could deliver the data we need to either dismiss this doomsday or confirm we're living on borrowed time. Until then, the Big Rip remains a haunting what if, a reminder that the universe's greatest mysteries aren't just academic. They might hold the keys to our ultimate fate. We tend to think of dark energy as a recent player in the cosmic drama, stepping onto the stage only after billions of years of gravity's dominance. But what if its fingerprints have been there all along, hidden in the universe's earliest moments? Let's rewind to the first fraction of a second after the Big Bang, a period called inflation, when the cosmos expanded exponentially faster than the speed of light. For decades, physicists attributed this explosive growth to a different kind of energy, the inflatoned field. But here's the twist. Some theories now suggest dark energy might have played a role even then. Picture this, the same repulsive force accelerating galaxies today could have been active in those primordial instants, a sort of cosmic echo across time. One provocative idea posits that dark energy isn't just a latecomer but a relic of inflation itself, leftover energy lingering in the vacuum of space long after the inflatoned field faded. If true, it would mean dark energy has been shaping the universe's destiny since the very beginning, lying dormant until conditions were right for it to reawaken. This reshuffles the cosmic timeline in startling ways. Take the so-called cosmic dark ages, the murky epoch between the Big Bang's afterglow fading and the first stars flickering to life. For millions of years, the universe was a cold, quiet expanse of hydrogen gas, barely disturbed, or so we thought. New simulations hint that dark energy, even in small amounts, might have subtly influenced how matter clumped together during this era. Tiny variations in its strength could have steered the formation of the first galaxies, like an unseen hand nudging the cosmos toward the structures we see today. But the most radical theories go further. Could dark energy's presence explain why the universe looks so eerily uniform on large scales? Inflation was invented to solve this horizon problem. How regions of space too distant to have ever interacted somehow share identical properties. But some researchers wonder, what if dark energy's repulsive force, acting intermittently across cosmic history, provided an alternative smoothing mechanism? It's a long shot, but if verified, it would mean dark energy didn't just accelerate the universe, it helped sculpt its very blueprint. Of course, testing these ideas is a formidable challenge. The only witnesses to the early universe are the cosmic microwave background and the faintest, most ancient galaxies. Yet upcoming telescopes like the James Webb Space Telescope are probing these relics with unprecedented precision, hunting for anomalies in the distribution of matter or the timing of star formation that might betray dark energy's early influence. Whether these speculations hold up or not, one thing is clear. Dark energy's story might be far older than we ever imagined. If it was there at the dawn of time, silently shaping events behind the scenes, then our understanding of cosmic history is due for a rewrite, one that could reveal connections between the universe's birth and its accelerating death. What if everything we think we know about dark energy is skewed, not because our instruments are wrong, but because we're stuck in a cosmic blind spot? This is the void hypothesis, a startling idea that flips the script on the accelerating universe. Picture our galaxy floating in a vast, bubble-like region of space where matter is unusually sparse, a cosmic desert billions of light-years wide. In such a void, gravity's pull would be weaker than average, making it seem like distant galaxies are fleeing faster than they actually are. The illusion. Dark energy might not be as powerful as we think. we could be mistaking our local emptiness for a universal force. The math behind this is deceptively simple. In general relativity, the density of matter curves spacetime, shaping how galaxies move. If we're inside an underdense region, the surrounding walls of denser space would act like a hill, pushing galaxies away from us faster than expected. Observers in this bubble would measure accelerated expansion, no dark energy required. It's like standing in a valley and assuming the whole world slopes downward because you can't see the mountains. Critics pounce on two glaring holes in this theory. First, voids this massive are incredibly rare in cosmological simulations, so rare that finding one by chance feels like winning the lottery. Second, even if we're in a void, it shouldn't perfectly mimic dark energy's signature across all observations. Yet some anomalies persist. The Hubble constant, which measures the universe's expansion rate, shows a puzzling tension. Local measurements disagree with predictions based on the cosmic microwave background. Could a giant void explain this mismatch? Proponents point to the cold spot, a strange billion-light-year-wide region in the cosmic microwave background that's unusually empty. If such structures exist, perhaps our corner of the cosmos is part of something similar. But proving it would require mapping the distribution of matter on scales beyond current surveys, something upcoming projects like the Dark Energy Spectroscopic Instrument aim to tackle. The void hypothesis forces a humbling question. Are we cosmic homebodies mistaking our neighborhood for the entire universe? If true, it wouldn't just downplay dark energy, it would remind us how much our view of reality depends on where we're standing. Until we peer deeper into the cosmos's scaffolding, this theory remains a tantalizing what-if, challenging us to consider whether the greatest mystery in physics is even real or just a trick of the light. At the heart of quantum mechanics lies a bizarre truth: empty space is never truly empty. Even in a perfect vacuum, particles flicker in and out of existence like cosmic static, their fleeting lives governed by the uncertainty principle. These quantum fluctuations, as they're called, aren't just mathematical quirks, they're real, measurable phenomena with tangible energy. And here's where things get wild. This vacuum energy might be the hidden engine behind dark energy's relentless push. Think of space as a frothing sea with virtual particles, electron-positron pairs, quarks, even entire atoms popping into reality for unimaginably short instants before vanishing again. According to quantum field theory, this chaotic dance should fill every cubic centimeter of the universe with energy. In fact, when physicists calculate how much energy these fluctuations should generate, the number is enormous, enough to rip apart galaxies in seconds. But when we compare this to the actual observed strength of dark energy, something doesn't add up. The theoretical prediction overshoots reality by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the most embarrassing mismatch in all of science. This discrepancy isn't just a small oversight. It's a glaring sign that our understanding of quantum physics and gravity might be fundamentally flawed. Some theorists argue the problem lies in how we're summing up these infinite quantum fluctuations. Others suggest gravity could somehow cancel out most of this vacuum energy, leaving only the tiny fraction we detect as dark energy. But no one knows how this cancellation would work. It's like tuning a radio to pick up one station while somehow silencing every other frequency in the universe simultaneously. Then there's the unsettling possibility that we're missing something deeper. Could quantum mechanics itself need rewriting on cosmic scales, or does the answer lie in string theory's extra dimensions, where much of this vacuum energy might leak away? The challenge is so profound that Nobel laureate Steven Weinberg called it the one real crisis facing theoretical physics. What makes this puzzle even more frustrating is that vacuum energy fits some observations eerily well. The cosmological constant Einstein's description of space's innate energy aligns with dark energy's apparent uniformity across the cosmos. But until we can bridge the gap between theory and observation, this connection remains tantalizingly out of reach. Upcoming experiments might finally crack the case by probing the quantum foam with ultra-precise measurements of Casimir forces, where quantum fluctuations push tiny metal plates together, or hunting for anomalies in high-energy particle collisions. We could uncover hints of how vacuum energy really behaves. Until then, dark energy's quantum roots remain one of the greatest unsolved mysteries in physics, a reminder that sometimes the emptiest places hold the biggest secrets. Dark energy and dark matter, two names that sound like cosmic counterparts, yet they couldn't seem more different. One is an invisible glue holding galaxies together with its gravitational pull. The other is an unseen force pushing the universe apart. But what if these two mysteries are secretly connected? Some physicists suspect they might be two sides of the same coin, a hidden relationship that could rewrite our understanding of the cosmos. Take the idea of a unified dark fluid, a theoretical substance that changes behavior depending on the environment. Imagine a cosmic chameleon acting like dark matter in the dense hearts of galaxies, where gravity dominates, but shifting into dark energy in the vast emptiness between them. This isn't just a wild guess. Models like Chaplygin gas, a hypothetical fluid with negative pressure, attempt to describe exactly that. At high densities, it clumps like dark matter. At low densities, it repels like dark energy. The allure is obvious, one elegant solution for both puzzles, yet challenges loom. Observations of colliding galaxy clusters, like the famous Bullet cluster, show dark matter behaving like a separate entity, slowing down during collisions while ordinary gas heats up and lags behind. If dark matter and dark energy were truly unified, wouldn't their effects blend seamlessly? Critics argue that these cosmic crime scene snapshots don't fit the fluid model. But proponents counter that we might be missing subtler interactions, like the fluid's viscosity or temperature variations, that could explain the discrepancies. Another twist comes from scalar fields, hypothetical entities that permeate space and could morph under different conditions. Picture a vast ocean where dark matter is the water's weight pressing down, and dark energy is the tide rising and pushing outward. Theories like quintessence, normally invoked for dark energy, have been stretched to include dark matter-like behavior when the field clusters in specific ways. The math is complex, but the payoff could be revolutionary. A single framework explaining both the universe's structure and its accelerating expansion. Then there's the holographic principle, a radical idea borrowed from black hole physics. It suggests that dark energy and dark matter might be projections of information encoded on the universe's boundary, like shadows cast by a deeper, hidden reality. In this view, their apparent differences could stem from how we perceive them, not their true nature. It's speculative, but it hints at how deeply these enigmas might be intertwined. For now, the link remains unproven, but every new observation, from the distribution of galaxies to subtle ripples in space-time, offers another piece of the puzzle. Whether dark energy and dark matter are long-lost cosmic siblings or entirely separate phenomena, their connection could hold the key to the universe's grand design. Picture the universe as a cosmic mirage, a three-dimensional projection of information encoded on a distant, two-dimensional boundary. This is the holographic principle, one of the most radical ideas in modern physics, and it might hold the key to unraveling dark energy's secrets. Born from the study of black holes, where physicists discovered that all the information inside them could be perfectly stored on their event horizons, the principle suggests something staggering. Our entire reality, with its galaxies, stars, and planets, might be no more than a hologram, a shadow cast by data scribbled on the edge of space-time itself. Now apply this to dark energy. If the universe truly behaves like a hologram, then its accelerating expansion could be a side effect of how information is processed at the cosmic horizon, the farthest edge of the observable universe. Think of it like a computer struggling to render a game as the graphics become more complex. As the universe expands, the code at the boundary might need to stretch to cover the growing volume, manifesting as dark energy's repulsive force. In this view, dark energy isn't a substance or a field, it's a glitch in the cosmic operating system. The math behind this is mind-bending. Theoretical models show that the holographic principle naturally generates a term resembling dark energy in Einstein's equations with a strength close to what we observe. It's as if the universe's expansion is tied to its information storage limits, a cosmic version of running out of memory, but skeptics raise tough questions. If this is true, why does dark energy's effect seem so uniform across space? Shouldn't there be variations, like pixelation in an overstretched image? Some theorists propose an even wilder twist. The holographic principle might explain why the vacuum energy calculated from quantum mechanics is so absurdly large compared to observed dark energy. In this scenario, most of that energy is locked at the boundary, invisible to us, while only a tiny fraction leaks into our 3D reality, like a hologram filtering out noise to project a clean image. It's a tantalizing fix for physics' biggest numerical mismatch, but proving it would require detecting subtle anomalies in the fabric of spacetime itself. Experiments are already underway. Gravitational wave observatories like LIGO and the future LISA mission could uncover hints of holographic noise, tiny fluctuations in spacetime that betray its underlying pixelated nature. Meanwhile, precise measurements of the cosmic microwave background might reveal patterns better explained by a universe encoded on a distant surface than by traditional physics. Whether the holographic principle holds up or not, its appeal is undeniable. It dares to ask if dark energy isn't just a mystery to solve, but a clue, a sign that we're glimpsing the edges of a deeper reality, one where information, not matter or energy, is the true currency of the cosmos. If right, it wouldn't just explain dark energy, it would redefine existence itself. Hidden in the faint glow of the cosmic microwave background, the afterimage of the Big Bang whispers of dark energy's secrets. This ancient light, traveling for nearly 14 billion years, carries imprints of every force that shaped the universe, including the subtle fingerprints of whatever dark energy truly is. The patterns we see aren't random. They're a cosmic barcode revealing how matter clumped together in the early universe and how dark energy later pried it apart. One of the most tantalizing clues comes from the CMB's temperature fluctuations, those tiny variations in heat that map the infant cosmos's density. According to Einstein's equations, dark energy should have left a specific signature in these patterns by smoothing out certain large-scale ripples as the universe expanded. And sure enough, when scientists compare observations from missions like Planck and WMAP to theoretical predictions, they find a telltale damping effect, like someone pressed a faint but deliberate thumbprint across the fabric of space. But the CMB holds deeper mysteries. Take the infamous cold spot, a bizarre patch of sky where temperatures dip unexpectedly. Stretching over 1 billion light-years, this anomaly defies easy explanation. Some researchers suggest it could be a cosmic void, a vast emptiness where dark energy's repulsive push left fewer galaxies to form. Others propose it's evidence of a collision with another universe in the multiverse, a scenario where dark energy's behavior might differ beyond our cosmic horizon. The most unsettling possibility, that the cold spot isn't an anomaly at all, but a sign that dark energy's strength varies across space, warping the universe in ways we haven't yet learned to read. Then there's the lensing effect, the way the CMB's light bends as it passes through the web of dark matter and dark energy. By measuring these distortions, astronomers can reconstruct how dark energy stretched the cosmos over time. Recent data hints at something peculiar. The lensing signal is slightly stronger than expected, as if dark energy's grip tightened more quickly in certain eras. Could this mean its influence isn't constant but evolves, growing stronger or weaker in cycles we've yet to decipher? The stakes are high. If dark energy's imprint on the CMB doesn't match our models, it could upend cosmology's standard playbook. Missions like the Simons Observatory and next-generation CMB telescopes are now hunting for finer details, polarization patterns, ultra-faint ripples that might reveal whether dark energy is a single force, a dynamic field, or something even stranger. Every new pixel in this cosmic snapshot brings us closer to answers, or deeper into the unknown. What makes these clues so powerful is their age. The CMB froze dark energy's shadow in time when the universe was a mere 380,000 years old. If we can decode it, we're not just studying dark energy today, we're reading its diary from the dawn of existence. And that might be the only way to understand why the cosmos is tearing itself apart. Imagine the early universe as a seething cosmic soup, trillions of degrees hot, where matter and energy were locked in a violent tug of war. Particles crowded together, pushed apart by radiation pressure, then pulled back by gravity, creating vast sound waves that rippled through the infant cosmos. Then suddenly everything froze. Around 380,000 years after the Big Bang, the universe cooled enough for atoms to form, releasing the light we now see as the cosmic microwave background. But those primordial sound waves, they left behind a hidden ruler etched into the fabric of space itself, a pattern called Baryon acoustic oscillations. Here's where it gets fascinating. Those ancient pressure waves stamped a predictable scale into the distribution of matter, like a cosmic fingerprint. We can still see it today. Galaxies tend to cluster at specific distances from each other, roughly 500 million light-years apart. This isn't random. It's the fossilized echo of those early sound waves, a yardstick that dark energy has been stretching over billions of years. By measuring how much this ruler has expanded, scientists can track dark energy's relentless push with stunning precision. Enter DAISY, the dark energy spectroscopic instrument. Mounted on a telescope in Arizona, DAISY is mapping millions of galaxies, quasars, and stars in unprecedented detail. Its goal, to measure baryon acoustic oscillations with such accuracy that we might finally spot variations in dark energy's strength across cosmic time. Think of it like listening to a symphony where each note reveals how fast the universe expanded at a different epoch. Earlier surveys, like the Sloan Digital Sky Survey, gave us the first rough sketches of these oscillations. DAISY is composing the full orchestral score, but why does this matter? Because baryon acoustic oscillations offer something rare in cosmology, a measurement that's almost immune to systematic errors. Unlike supernova, which depend on understanding stellar explosions, or galaxy clusters, which rely on complex physics, this cosmic ruler is rooted in straightforward sound wave physics from the universe's infancy. It's like finding a perfectly preserved dinosaur bone instead of trying to reconstruct the creature from scattered teeth. Yet even here, surprises lurk. Recent DAISY data hints that dark energy's influence might not be perfectly uniform, a whisper that it could evolve over time or interact with other forces. If confirmed, this would shatter the simplest version of the cosmological constant, forcing us to consider wilder ideas like quintessence or even entirely new physics. What's truly astonishing is how much rides on these ghostly vibrations from the dawn of time. They're not just relics, they're active tools, letting us measure the invisible hand shaping the universe's fate. And with every new galaxy mapped, we're not just reading the cosmos's past, we're decoding its future. Galaxies aren't just scattered randomly across the cosmos, they form vast, intricate webs with clusters and filaments stretching billions of light-years. But what if this cosmic architecture wasn't shaped by gravity alone? Lurking in the background, dark energy might have been quietly pulling the strings, stifling the growth of these colossal structures in ways we're only beginning to understand. Picture the early universe as a construction site where matter slowly clumps together under gravity's pull. forming denser regions that eventually become galaxies. For billions of years, this process dominated, with dark matter acting as scaffolding for gas and stars to gather. But as the universe expanded, dark energy's repulsive force grew stronger, working against gravity's tireless efforts. Think of it like trying to build a sandcastle. As the tide rolls in, each wave of expansion makes it harder for structures to hold their shape. The evidence lies in the void. These enormous, nearly empty regions between galaxy clusters are far larger and more numerous than traditional models predict. Simulations that ignore dark energy show a universe clumped more densely, like bread rising unevenly. But when dark energy's push is factored in, the virtual cosmos better matches what we see: sparser, with galaxies more isolated. It's as if dark energy put a speed limit on cosmic growth, preventing matter from gathering too tightly. Yet some observations complicate this picture. Take superclusters, colossal groupings of galaxies spanning hundreds of millions of light years. These giants shouldn't exist if dark energy's influence has been constant. Their sheer size suggests gravity held sway longer than expected, or perhaps dark energy's strength varied over time. Then there's the case of ultra-diffuse galaxies, fragile, sprawling structures that somehow survived dark energy's stretching grasp. Their existence hints at a delicate balance between forces, where local conditions shielded them from the worst effects. What's most surprising is the timing. Dark energy only became dominant around 5 billion years ago, relatively recently in cosmic terms. Yet its subtle influence might have been at work far earlier, like an invisible hand gently steering matter into place. Some theorists propose that without dark energy's restraining effect, supermassive black holes would have grown even larger, galaxies would be more tightly packed, and the universe's large-scale structure would look radically different. The implications are profound. If dark energy truly sculpted galaxy formation, then the cosmos we see today isn't just the product of gravity's pull, but also of an opposing force we still don't fully comprehend. Upcoming telescopes like the Nancy Grace Roman Space Telescope will map millions of galaxies in unprecedented detail, searching for signs of this cosmic tug of war etched into their distribution. The answers might rewrite not just the story of galaxies, but our entire understanding of the forces that shaped them. What if our universe's dark energy isn't a fundamental law, but a cosmic roll of the dice? This is the spine-tingling premise of the multiverse theory, the idea that our reality might be just one bubble in an infinite froth of universes, each with its own random physical constants. In most of them, dark energy could be so weak that gravity crushes everything into black holes, or so strong that matter is ripped apart before stars even form. Ours, by sheer chance, landed in the narrow Goldilocks zone where galaxies and life could exist. It's a staggering thought. The very force accelerating our universe's expansion might not be inevitable but a fluke. The math behind this is as elegant as it is unsettling. String theory, our leading candidate for a theory of everything, suggests there could be 10 to the power of 500 possible vacuum states, each representing a universe with different fundamental forces. Dark energy's value in this landscape isn't fixed. It's like a dial that could have landed anywhere. Most settings would render life impossible. Ours improbably didn't. This line of reasoning leans on the anthropic principle. We observe a universe suitable for life because we couldn't exist in one that wasn't. It's not design, it's survivor bias on a cosmic scale. But critics slam this as a cop-out. If every physical mystery can be explained by "we got lucky in the multiverse," does science lose its power to explain anything? Nobel laureate Paul Steinhardt calls it the ultimate seat of the pants argument, a retreat from the hard work of finding deeper laws. Others counter that the multiverse isn't philosophy, it's a testable hypothesis. If other universes exist, their collisions could leave scars in our cosmic microwave background, or gravitational wave observatories might detect echoes of bubble universes forming. The challenge is separating these signals from noise, like listening for a whisper in a hurricane. The stakes couldn't be higher. If the multiverse is real, dark energy's value isn't a puzzle to solve but a fact to accept, like living on a mountain and wondering why the air is thin. But if it's wrong, we're back to square one. Why does the universe have this exact life-allowing amount of dark energy, down to 1 part in 10 to the power of 120? Some theorists seek middle ground, proposing that an undiscovered law locks dark energy's value, making our universe inevitable. Others suggest it's dynamic, evolving toward life-friendly conditions over cosmic time. For now, the debate straddles the line between profound insight and untestable speculation. But whether the multiverse is science's next revolution or a dead end, one thing's clear: dark energy's mystery is forcing us to ask questions we never thought science would or could confront. The idea that dark energy might be slowly fading away, decaying into something else entirely, offers a glimmer of hope against the universe's grim fate. Forget the big rip's terrifying finale for a moment. What if dark energy isn't a relentless, unchanging force but a temporary one, quietly dissipating over cosmic time? This isn't just wishful thinking. A handful of bold theories suggest dark energy could be transforming into ordinary particles, dark matter, or even entirely new fields, rewinding its own destructive influence. Take the concept of phantom energy decay, a twist on the doomsday scenario where dark energy's strength grows infinitely. Some models propose that phantom energy, instead of intensifying forever, might reach a tipping point where it destabilizes like a stretched rubber band snapping back. In this case, the repulsive force could decay into massive particles, flooding the universe with matter and radiation. The result, instead of tearing space-time apart, dark energy would eventually fizzle out, leaving behind a colder, quieter cosmos. Then there's the quintessence angle, where dark energy isn't a static force but a dynamic field that can lose energy over time. Picture a pendulum gradually slowing down. As the quintessence field loses momentum, its repulsive push weakens, allowing gravity to regain dominance. Some versions of this theory even allow for dark energy to eventually turn attractive, pulling the universe back toward a big crunch, a dramatic reversal of its current expansion. But how do we test these ideas? The key lies in precision measurements of the universe's expansion rate over billions of years. If dark energy is decaying, its influence should leave subtle fingerprints in the distances between supernovae, the clustering of galaxies, and the bending of light around massive objects. Projects like the upcoming Euclid Space Telescope are designed to hunt for these clues, mapping the cosmic web with unprecedented detail to spot any deviations from dark energy's expected behavior. Yet challenges remain. If dark energy's decay is slow, say, over trillions of years, its effects might be too faint to detect with current technology, and alternative explanations like undiscovered interactions between dark energy and dark matter could muddy the waters. Still, the possibility that the universe's fate isn't set in stone is too tantalizing to ignore. Whether dark energy is eternal or ephemeral, the answer could redefine not just our future, but the very laws that govern reality. What if the most exotic objects in the universe aren't black holes at all, but something far stranger, forged from dark energy itself? Enter the realm of hypothetical dark energy stars, cosmic oddities that could rewrite our understanding of space's most extreme environments. Picture a gravistar, short for gravitational vacuum star, a bizarre alternative to black holes where an ultra-thin shell of matter encases a core of pure dark energy. Instead of collapsing into a singularity, these objects would hover on the edge of annihilation, their dark energy interiors exerting an outward pressure powerful enough to halt gravity's fatal crush. It's like balancing a bowling ball on the tip of a needle, an impossible equilibrium that defies everything we know about stellar death. Then there's the even more speculative black star, a theoretical object that never fully forms a black hole's event horizon. As matter collapses, dark energy's repulsive force counteracts gravity's pull, creating a frozen, ghostly remnant, a star eternally trapped in the moment before becoming a black hole. Unlike the darkness of a singularity, black stars could emit faint, eerie radiation, a whisper of their near-death state. The implications are profound. If these objects exist, they might resolve black hole paradoxes like the information loss problem, where quantum data seemingly vanishes into oblivion. Instead of information being lost behind an event horizon, it could linger on a black star's surface, encoded in subtle quantum fluctuations. But how would we spot such exotic creatures? Gravitational wave observatories might hold the key. When black holes merge, they produce distinctive ripples in space-time, but a gravastar collision could leave a different fingerprint. Simulations suggest these events might generate echoes or prolonged, ringing signals as the dark energy core reacts violently to the merger. Some researchers even argue that certain anomalous gravitational wave detections, like those with unexpected frequency patterns, could hint at dark energy stars masquerading as black holes. Yet skepticism abounds. Critics point out that gravastars and black stars require fine-tuned conditions that might not occur naturally, and without direct evidence, they remain mathematical curiosities, ghosts in the equations. But as telescopes peer deeper into the hearts of galaxies and gravitational wave detectors grow more sensitive, we might finally catch a glimpse of these dark energy phantoms. Whether they're real or not, their very possibility forces us to ask, could the universe's most destructive forces also birth its most bizarre creations? Einstein called it his greatest blunder, a mathematical fudge he scribbled into the equations of general relativity, then angrily crossed out. The year was 1917, and his theory of gravity predicted a universe that should either collapse or expand. But astronomers insisted the cosmos was static, unchanging. So Einstein added a term to his equations, the cosmological constant, a kind of anti-gravity that would perfectly balance the universe, holding it in equilibrium. Then, 12 years later, Edwin Hubble proved the universe wasn't static at all, it was expanding. Einstein tore up his constant in disgust, calling it unnecessary. But the real irony, that discarded idea might be the key to dark energy, the most mysterious force in the cosmos. Think of it like this. Einstein's cosmological constant represented an innate energy woven into the fabric of space itself, a property of the vacuum that wouldn't dilute as the universe expanded. Sound familiar? That's exactly how dark energy behaves today. In the late 1990s, when astronomers discovered the universe's expansion was accelerating, they realized Einstein's mistake wasn't a mistake at all. His discarded term fit the data perfectly, like a key sliding into a lock that had been hidden for decades. But here's where it gets complicated. The cosmological constant was meant to be static, a fixed value balancing gravity's pull. Dark energy, as we observe it, seems similarly unchanging, yet some data hints it might not be. If dark energy varies over time, then Einstein's elegant solution isn't just resurrected, it's evolved. Some theorists now suggest the cosmological constant might have been the first glimpse of something far deeper, a dynamic field or a shadow of quantum vacuum energy we still don't fully grasp. Einstein himself might have been torn. On one hand, his equations predicted dark energy long before we had the tools to detect it, a testament to his unparalleled intuition. On the other, he abandoned the idea because it lacked a physical explanation, and to this day we still don't have one. The cosmological constant's value, derived from modern observations, is shockingly small compared to quantum physics predictions, off by a factor of 10 to the power of 120. That's not just a minor discrepancy, it's the largest mismatch in science, meaning Einstein's blunder might be pointing to a gap in our understanding even bigger than dark energy itself. What makes this story so compelling isn't just the irony, it's the lesson. Science isn't about being right the first time. It's about asking the right questions, even if the answers take a century to uncover. Einstein's greatest blunder might yet become his greatest triumph, not because he nailed it, but because he left a clue that future generations couldn't ignore. And somewhere in the gap between his intuition and our ignorance, the next revelation might be waiting. The race to unravel dark energy's secrets is entering uncharted territory. Cutting-edge missions like the Euclid Space Telescope and the Vera Rubin Observatory's Legacy Survey of Space and Time aren't just upgrades, they're cosmic game-changers, armed with technology that would have seemed like science fiction just decades ago. Euclid, launched in 2023, is essentially a dark energy detective floating in space. With its razor-sharp infrared eye, it's mapping over 1 billion galaxies across 10 billion years of cosmic history, creating the most detailed 3D map of the universe ever attempted. What makes Euclid revolutionary isn't just its scale, it's how it connects the dots. By measuring two key phenomena simultaneously, Baryon acoustic oscillations and weak gravitational lensing, it's cross-examining dark energy's effects like never before. Gravitational lensing, where massive objects bend light like a cosmic magnifying glass, takes center stage in this investigation. The Vera Rubin Observatory's LSST camera, the largest digital camera ever built for astronomy, will capture this phenomenon with staggering precision. Every few nights, its 3.2 gigapixel eye will scan the entire southern sky, spotting subtle distortions in the shapes of billions of galaxies. These distortions aren't random, they're the fingerprints of dark matter's distribution, which in turn reveals how dark energy stretches the cosmic web. Unlike previous surveys that studied patches of the sky, LSST Panorama approach could reveal whether dark energy's push varies across different regions of the universe, a clue that might shatter the cosmological constant paradigm. But the real power emerges when these missions collaborate. Euclid's deep space precision combined with LSST panoramic view creates a multi-scale cosmic microscope. Imagine reconstructing the universe's expansion history not just through snapshots but as a continuous film, watching how dark energy's influence changed across cosmic epochs. There's also WFIRST, NASA upcoming infrared telescope designed to measure the light from 1,000 supernovae annually while mapping dark matter in 3 dimensions. Together, these instruments form an unprecedented trifecta, triangulating dark energy's nature through independent methods. If their findings converge, we might finally have an answer. If they diverge, well, that could mean something even more exciting. That dark energy is stranger than we imagined. The technological leaps behind these missions are staggering. Euclid's onboard detectors can spot galaxies so faint their light is just a few photons above background noise. LSST data pipeline will process 30 terabytes nightly, equivalent to scanning the entire Library of Congress twice over every observation session. To handle this deluge, scientists are employing machine learning algorithms that can recognize subtle patterns human eyes would miss. Some teams are even training AI to predict where supernova will appear, maximizing precious telescope time. What makes this era unique isn't just the scale of data, but how it tests competing theories simultaneously. Quintessence models predict subtle variations in dark energy's strength that these telescopes might catch. Modified gravity theories forecast specific patterns in how galaxy clusters move that Euclid could confirm or rule out. Even wild ideas like interacting dark sectors, where dark energy talks to dark matter, leave distinctive marks in the cosmic web that LSST vast survey could reveal. We're not just gathering more data, we're conducting the universe's most comprehensive physics experiment. The implications stretch beyond astronomy. If dark energy behaves differently than Einstein's equations predict, it could send shockwaves through particle physics, quantum theory, even philosophy. These missions are more than telescopes, they're time machines, letting us watch the universe evolve while testing whether our fundamental laws hold across billions of years. Whatever they find, one thing's certain: the cosmic dark energy saga is about to get much more interesting. Imagine a future so distant that the stars we see tonight are gone, not just faded but vanished beyond an unreachable horizon. This is the inevitable consequence of dark energy's relentless push, a fate that doesn't just reshape the cosmos but could erase the very possibility of life within it. If the universe keeps accelerating, galaxies beyond our local group will eventually be flung so far away that their light can never reach us. The night sky, now glittering with countless stars, will grow darker and darker until only a handful of nearby galaxies remain visible. For any civilization surviving into this era, the universe will feel profoundly lonely, a vast, empty expanse where the ingredients for life are scattered too thinly to ever reunite. But could life endure in such a desolate future? The answer depends on dark energy's true nature. If it's a constant force, as Einstein's cosmological constant suggests, then galaxies within our local group, bound by gravity, will stay together, forming a kind of cosmic island in an ever-expanding void. Stars will still burn, planets will still orbit, and in theory, life could persist. But there's a catch. Over trillions of years, even these islands will face a slow-motion crisis. As stars exhaust their fuel and die, new ones can only form if there's enough gas left to collapse. Yet in a dark energy-dominated era, that gas is relentlessly diluted, spread thinner and thinner until star formation grinds to a halt. The universe becomes a graveyard of dead stars and black holes, with no energy sources left to sustain life. Now consider a darker scenario. If dark energy isn't constant but phantom energy, growing stronger over time, the stakes are far worse. Galaxies, stars, even atoms would be torn apart in the Big Rip. But even before that catastrophic end, civilizations would face an insidious threat: the stretching of space itself. Complex structures, from planets to DNA, rely on electromagnetic forces to hold them together. If dark energy's push overwhelms these forces, the bonds between molecules could weaken, making chemistry, and by extension life, impossible long before the final rip. Yet some theorists refuse to surrender to pessimism. Freeman Dyson once speculated that advanced civilizations might adapt by harvesting energy from black holes, stretching their survival into the far future. Others propose that life could exist in forms we can't yet imagine, free from the constraints of planets or stars. But these are gambles against entropy itself, a battle where the odds grow worse with every passing eon. The cruelest irony: dark energy's dominance might be what made life possible in the first place. Without its repulsive force, gravity could have collapsed the universe into a black hole long before galaxies or stars formed. We exist because dark energy delayed that collapse, only to threaten us with isolation later. It's a cosmic catch-22. The same force that allowed life to emerge may ultimately render the universe lifeless. What's truly humbling is the timescale. Humanity has existed for a blink of cosmic time, yet we're already grappling with a fate that unfolds over trillions of years. Whether life can outlast dark energy's grip is more than a physics puzzle. It's a test of ingenuity against the universe's coldest, most impersonal laws. And if the answer is no, it reminds us how rare and fragile our moment in the cosmic story really is. What if dark energy isn't native to our universe at all? Imagine it seeping in from hidden dimensions, invisible realms folded into the fabric of reality, just beyond our perception. This isn't science fiction. It's a serious possibility in string theories, brain-world scenarios, where our entire cosmos could be a three-dimensional membrane floating in a higher dimensional space. In this mind-bending framework, dark energy's mysterious push might not come from within our universe but from something far stranger: the gravitational tug of another reality bleeding into ours. String theory suggests the existence of at least 10 dimensions, most curled up so tightly we'd never notice them. But in brain-world models, some of these extra dimensions could be vast, parallel universes hovering just out of reach. Picture our universe as a slice of bread in a cosmic loaf, with other brains hovering millimeters away in a dimension we can't see. Gravity, unlike other forces, might leak between these brains, and if a neighboring universe's gravity spilled into ours, it could manifest as the repulsive force we call dark energy. It's like feeling the wind from a fan in another room. You can't see the source, but its effects are unmistakable. One version of this idea comes from the ekpyrotic universe theory, which proposes that our Big Bang wasn't a singular creation event but a collision between brains in higher dimensional space. The energy from that collision could have left behind a lingering repulsion, dark energy's fingerprint. Even more intriguing, if these brains are still drifting apart in extra dimensions, their separation could generate the steady, accelerating expansion we observe today. But how would this fit with string theory's tangled web of possibilities? In some models, the extra dimensions aren't static. They vibrate, shift, or warp over time. Dark energy's apparent consistency might actually mask subtle fluctuations caused by these unseen dimensional dynamics. For instance, if a higher dimensional bulk space were expanding, our brain's dark energy could gradually strengthen or weaken, echoing the behavior of quintessence. It's a cosmic game of telephone where shifts in one dimension ripple into ours as phantom forces. Critics argue this is speculative sleight of hand, explaining one mystery by invoking another. Without direct evidence of extra dimensions, brain-world dark energy risks being untestable, but supporters point to potential clues. If dark energy interacts with higher dimensions, it might leave faint imprints in gravitational waves or distort the cosmic microwave background in specific ways. Future experiments like pulsar timing arrays or next-generation particle colliders could hunt for these anomalies, turning a wild hypothesis into hard science. The stakes are cosmic. If dark energy truly leaks from other dimensions, it wouldn't just solve a physics puzzle, it would prove we're living in a multiverse, a tiny corner of a reality far vaster and weirder than we ever dreamed. And that realization might be the first step toward unraveling the deepest layers of existence. There's something deeply unsettling about dark energy's numbers, not just that they exist, but that they're shockingly precise. The universe's expansion rate, the density of dark energy, even the timing of its dominance, they all align in a way that feels suspiciously convenient. If dark energy were even slightly stronger, galaxies would never have formed. Slightly weaker, and gravity would have crushed everything into a black hole long before life could emerge. This razor-thin margin for error is more than a curiosity. It's a puzzle that forces us to ask, why does dark energy seem tailor-made for our existence? One answer lies in the anthropic principle, the idea that the universe's fundamental constants must allow for observers like us because, well, we're here to notice them. Think of it like a cosmic version of survivorship bias. If the laws of physics were even slightly different, we wouldn't exist to ponder them. This isn't about purpose or design, it's about sheer probability. In a hypothetical multiverse where every possible combination of physical constants exists, we inevitably find ourselves in one of the rare universes where conditions are just right for life. The unsettling implication, dark energy's perfect value might not be a law of nature, but a lottery ticket we happen to draw. But the anthropic principle leaves many scientists cold. To some, it feels like giving up an admission that we'll never find a deeper reason for dark energy's fine-tuning. Physicist Paul Davies once called it a counsel of despair, arguing that it replaces explanation with coincidence. After all, if every mystery can be hand-waved away by saying, "we got lucky," does science lose its power to uncover real answers? The counterargument is equally compelling. If the multiverse is real, then the anthropic principle isn't a cop-out, it's a predictive framework. It tells us where to look for life in a vast ensemble of universes and why our local patch looks so improbably hospitable. Yet there's another, even wilder possibility. What if dark energy isn't a fixed constant at all, but something that evolves toward life-friendly values over time? Some versions of quantum mechanics suggest the universe might select its own laws through observation, a process called cosmological natural selection. In this view, dark energy's value isn't random, it's the result of an as-yet unknown feedback loop that biases the cosmos toward conditions ripe for complexity. It's a radical idea, but so was dark energy itself before we stumbled onto it. The stakes here are cosmic. If the anthropic principle holds, our universe is one of countless accidents, and dark energy's fine-tuning is a fluke. If there's a deeper law at work, we might be on the brink of a revolution as profound as relativity or quantum theory. For now, the debate rages on, fueled by every new telescope observation and supercomputer simulation. But one thing's certain, dark energy's Goldilocks perfection isn't just a quirk, it's a riddle that forces us to confront whether our universe is inevitable, improbable, or something stranger than we've dared to imagine. Gravitational waves, the ripples in spacetime caused by cosmic cataclysms like black hole collisions, might hold secrets far deeper than we ever imagined. These faint tremors, first detected in 2015, aren't just messengers of violent events. They could be cosmic echoes of dark energy's hidden hand, especially when we listen to the oldest whispers from the early universe. Picture two black holes merging billions of years ago, sending waves racing across the cosmos. As those waves traveled through expanding space, dark energy's relentless push would have subtly stretched their wavelengths, leaving a telltale signature, one that future gravitational wave observatories are uniquely poised to decode. The key lies in frequency shifts. Just as a siren's pitch drops as it moves away from you, a phenomenon called the Doppler effect, gravitational waves from ancient mergers should carry an extra redshift, stretched not just by the universe's expansion but by dark energy's accelerating influence. Future detectors like LISA, the Laser Interferometer Space Antenna, will hunt for these distorted signals. Unlike ground-based observatories like LIGO, which catch high-frequency waves from recent mergers, LISA space-based sensors will tune into low-frequency ripples from supermassive black holes colliding when the universe was young. These primordial waves, having traversed eons of expanding spacetime, could reveal how dark energy's strength changed over cosmic history, like a tape recording of the universe's accelerating heartbeat. But the real breakthrough might come from combining gravitational wave data with other cosmic clues. When a neutron-star merger occurs, it spews light and gravitational waves simultaneously. By comparing the wave's arrival time with its electromagnetic counterpart, scientists can measure the universe's expansion rate independently of traditional methods. Any discrepancies could hint at dark energy's dynamic nature. Perhaps its influence wavers over time or interacts with gravity in ways Einstein never predicted. Already, anomalies in early LIGO Virgo data have sparked whispers of modified gravity theories, where dark energy isn't a force at all but a sign that relativity breaks down at cosmic scales. The most tantalizing possibility, gravitational waves from the cosmic dawn, the first black holes born in the universe's fiery infancy. These primordial mergers would have rippled through a cosmos barely 100 million years old when dark energy's grip was weaker. If detectors like the Einstein telescope or Cosmic Explorer can capture these ancient waves, they'll offer a snapshot of dark energy in its youth, revealing whether it's truly constant or evolved alongside the universe. It's like uncovering a childhood photo of a reclusive billionaire. Suddenly, the mystery has context, yet challenges loom. Gravitational wave astronomy is still in its infancy, and isolating dark energy's signal from background noise is like picking out a single voice in a roaring stadium. Advanced AI and next-generation detectors will need to filter out distortions from interstellar gas, galactic collisions, even quantum space-time foam. But if successful, we might finally glimpse dark energy's fingerprint on the fabric of reality itself, not as a theoretical phantom, but as a measurable force woven into the very waves that shake the universe. What makes this hunt so thrilling is its audacity. We're not just looking for dark energy's effects, we're listening for them, attuning our machines to the subtle warps in space-time it leaves behind. And if the whispers of those distant mergers carry the clues we hope for, they won't just illuminate dark energy, they'll redefine how we hear the cosmos. For centuries, science has operated under the assumption that four fundamental forces govern the universe: gravity, electromagnetism, and the strong and weak nuclear forces. But dark energy's existence throws a wrench into this tidy framework. What if it's not just an oddity, but a fifth fundamental force, one we've only just begun to detect? This isn't just a technicality. If confirmed, it would mean rewriting the textbooks on everything from particle physics to cosmology, forcing us to rethink reality's deepest rules. Take gravity's role in the cosmic dance. Einstein's theory of general relativity describes it as the curvature of space-time, a force that pulls matter together. But dark energy does the opposite. It repels, pushing space-time apart. If it's a new force, then relativity, our gold standard for understanding gravity, might be incomplete. Some theorists argue this could explain why quantum mechanics and gravity refuse to play nice in a unified theory. Dark energy might be the missing piece, a bridge between the infinitesimally small and the astronomically large. Or it could be something far stranger, a force that doesn't behave like the others at all, operating only on cosmic scales while remaining invisible in our everyday world. Then there's the unsettling possibility that dark energy isn't just another force, it's a sign that our understanding of forces themselves is flawed. In quantum field theory, forces arise from particles exchanging messenger particles, photons for electromagnetism, gluons for the strong force. But dark energy doesn't fit this model. It doesn't seem to have an associated particle, and its effects don't weaken with distance like gravity or electromagnetism. Instead, it grows stronger as the universe expands, as if woven into the fabric of space itself. This defiance of convention has led some physicists to propose radical alternatives like screened or chameleon fields, where dark energy's strength shifts depending on its environment, strong in the void between galaxies, weak within solar systems. The philosophical implications run even deeper. If dark energy is a fifth force, why did it remain hidden for so long? The other forces shape everything from atomic bonds to supernova, but dark energy's influence only became obvious when we peered across billions of light years. This selectivity raises haunting questions. Are there other forces lurking in the cosmos, invisible to us because their effects only manifest under conditions we haven't encountered yet? Could our entire framework of physics be a parochial snapshot, limited by the tiny sliver of reality we've observed so far? The stakes couldn't be higher. Confirming dark energy as a fifth force wouldn't just solve a cosmic mystery, it would redefine what we consider fundamental about the universe. And if it defies our current models entirely, the implications ripple beyond astronomy. Philosophy, metaphysics, even the way we conceptualize existence might need to adapt to a cosmos where the rules aren't just unknown, but fundamentally stranger than we ever imagined. From the eerie coincidence of dark energies timing to the mind-bending possibility of extra dimensions leaking into our universe, these 25 mysteries paint a humbling picture. We've barely scratched the surface of understanding the cosmos. Dark energy isn't just one puzzle, it's a labyrinth of unanswered questions, each more perplexing than the last. Why does it dominate now after billions of years of gravity's reign? Is it a quantum fluke, a fifth force, or something beyond our current physics? Could it be reshaping reality in ways we can't yet measure, or even signaling connections to other universes? Every discovery peels back a layer, only to reveal deeper enigmas waiting beneath. This isn't failure, it's inspiration. The gaps in our knowledge aren't empty spaces, they're invitations to explore, to question, to imagine. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." Dark energy embodies that promise. It reminds us that the universe isn't just stranger than we imagine, it's stranger than we can imagine. And that's what makes this journey so thrilling. So what's your take? Do you think dark energy is a constant force, or does it evolve over time? Could it be tied to the multiverse, or is it proof we need to rewrite physics from the ground up? Drop your wildest theories in the comments, because the next big breakthrough might not come from a lab or a telescope, but from a spark of curiosity shared and amplified. The cosmos is talking. Let's keep listening.